Hi everyone, Hussein is here from EJ Academy. Amir is here with me too. Hey Amir, how are
Hello,
you?
good. How are you today?
I'm good, thank you. So Amir, if you remember, last week we had another video. You helped me solve that video. It was about rate of change, and we use derivative and to solve that problem. Here I have another problem. This is also application of derivative. And so please help me to solve this problem as well. For the
Sure.
viewers, if you're interested also to see our last video, we put the link for that video somewhere on the screen here for you. So it's going to be easy for you to find that one. So this week, the problem that we're going to solve is this. Let me read the problem statement for you, Amir.
Sure.
So it's a 3D geometry. We have a cone-shaped reservoir with a radius of 2 meter and height of 8 meter contains water. So the radius at the top is 2 meter and the maximum height is 8 meter and it contains water. When the height of water in the reservoir is 5 meter, the rate of leaking is 0.5 cubic meter per second. Find the rate at which the height of water is changing. So it means that you have the rate of change of the volume. Now the problem is asking you to find the rate of change of the height. And of course, all of these changes are with respect to time.
Yes, yeah,
Yeah, so Amir, so please go ahead and show how you can and
absolutely.
you're going to solve this
Yeah,
problem.
this is an interesting problem. Uh, so the height of the water is 5 meter. So it's like around here, I can imagine.
Right.
So that's the level of the water, and there is a leakage here from the bottom of I think my pen is thick. Let me just do it. Adjust it. 0.5 cubic meter per second. So
Right.
the volume of water is reduced
Right.
based on this leakage.
As a result, the height also decreasing.
Correct.
The height
And
of
as a
water in the
result,
cone.
correct, the height is also decreasing. In other words, it means that the level of the top level of water is going down.
Right.
So, okay, let me name this radius where the water level is as r, lowercase
Yeah.
r, and this height
The
where
height
the
of
water,
water, not the height of the reservoir.
correct, as lowercase h. And we know that the height of the reservoir is h here.
Right.
Okay.
So just the viewer pay attention. Capital H and capital R are the height and the radius of the reservoir, and the small h and the small r are the height and the radius of the water in the reservoir, and it's changing.
Yes, thanks for emphasizing that. Okay, we have rate of change in the volume of the water. Okay, because of this leakage, it means that okay, we need to first know the volume of the water, which is inside a cone. So the volume of water is also a cone. Therefore, the volume of water is 1/3 of the area of the base of the cone, which is here.
Pi r squared.
Correct. Pi lowercase r squared times the height of the cone.
Water. The
Yeah,
height of the water.
correct. The height of the water here.
Right. Small h.
So I need to have dV over dt because we have a leakage there. But before that,
So that 0.5 is dV to dt.
correct.
The 0.5 that you wrote over there, right?
It's dV over dt. And since it's going out of the reservoir, it's going to be negative.
That's correct. Yeah, that's what I was thinking. Yeah.
And in the relationship for the volume, H and R are dependent, meaning that when we have, for example, the water level here, R is this one and H is this one, so they decrease together. But there is a relationship between H and R, which I'm gonna obtain. So we use the proportionality of triangles here to obtain the relationship between R and H. And we know that, okay, we have this larger triangle and then this smaller triangle, and they are proportional because they have one angle in common here and also one angle which is 90 degrees in common there. Therefore, we can use the proportionality theorem. From the big triangle to the small triangle, we have R of the big triangle over R of the smaller one is equal to H to lowercase h. And we know we know that the big R is 2 meters and the big H is 8 meters. Therefore, R is equal to H over 4.
Right.
So that's the relationship between these two parameters. So, and we know that both R and H are function of time. So let me just first replace R in this equation with H. Therefore, it's going to be 1/3 of pi R, which is H over 4 squared, as we obtained here, times H, which is pi over 48, 16 times 3 in the denominator, times H cubed. So that's the relationship of V in terms of H. So it is, oops, sorry, delete that. Pi over 48 H cubed. Okay, so far we obtained the volume of cone, volume of the water inside the cone, which is in terms of H. And H itself is a function of time.
Just wanted to add something. You could replace H with R, but you decided to replace R with H because the problem is asking for the to find the rate of change of height with respect to time, not the radius with respect to time.
Correct. Yes. Because we can see the height of the water. It's easier to. It's more intuitive. So since we have here dV over dt, and we want to have the rate of the change of height of water.
Height.
Yes. So it's like dH over dt here, which is of interest in this problem.
Right.
So I'm going to take the derivative of v with respect to time, as we have it here. So
right.
dv over dt is equal to, we know that v is in terms of h, and h is in terms of time. So I'm going to use chain rule here. So it's going to be dv with
That's an
respect
application
to,
of chain rule.
yes, and then dh with respect to time. And we know that this is of the answer, I mean the question. So we want to solve for that. Therefore, I need to obtain this term.
Right.
From, I call it number one, I call it number two. From one,
one is the relationship between V and H.
Correct.
Use that to.
Yeah. dv over dh, I just take the derivative. So it's going to be
it's
pi
a polynomial,
over,
it's easy.
Correct. Times 3h squared, or pi over 16h squared. So I call it number 3. So I put number 3 in number 2 in here. So from 2 and 3, I get dv over dt is equal to pi over 16h squared times dh over dt. We know that from the problem statement, the leakage is 0.5 cubic meter per second, or dv over dt is negative 0.5. So I'm going to put that in here.
And then at that time, the height is 5.
Yes, and
so you also know
time,
the height of water.
Yeah, it's given in the problem. So I'm going to actually substitute these numbers into the equation. Therefore, it's negative 0.5 is equal to pi over 16 times 5 squared, the height, which is 5, height of the water, and then times dh over dt.
Okay, the only unknown in this equation you wrote is dh over dt.
Correct, which is of question.
I'm going to rearrange the equation probably.
Yes, dh over dt is equal to negative 0.5 divided by pi over 16 times, let me just write it down as 25 times 25.
Okay, I have a calculator here. Let me do that.
Okay, thank you very much.
Negative 0.5, 16 divided by pi times 25. Okay, it is negative 0.102.
Yes.
And what would be the unit here?
Yeah, the unit. Let me just look at that. 0.5 is, let me use another color, cubic meter per second. In here, this is unitless. 25. Okay, this was height, 5 meters squared, so it is meter squared. So this meter is cancelled with this one, so we have just one m here, meter here. So it is meter per second.
Okay,
Which
makes
makes
sense, right? It's height,
yes,
change of height with
change
respect
of
to time,
height.
so meter per second.
Correct. Yes, and the
Okay,
negative
yeah,
is because the volume is the volume of water is decreasing. So
decreasing,
yeah,
right? Yeah, thank you, Amir. I appreciate it.
sure.
Yeah, that is awesome. All right. Thanks, thanks everybody for watching this video. I hope you learned something from this video, and I appreciate if you consider subscribing to our channel if you haven't already, and also hit the notification bell to get notified for future videos. And that is all for today. Until next video, bye everyone. Bye, Amir.
Bye. Thank you.